Welcome to the next session, which is on where we will kind of look at a typical architecture of an embedded system, and we will also look at basically an example of an embedded system. We'll take a little look at what is the software architecture which is popular and common in an embedded system. A few variety which you will see based on the class of the devices that are there. So that is what we are going to cover in the next hour or so. So getting started today in the modern systems that you see getting developed, the most popular microcontrollers are from the ARM family. So ARM has a wide range of embedded processors. They have a M series, which is a low-end microcontroller. Then they have something called an A series, which is slightly higher-end microprocessors. So they have a good spectrum of devices. I mean, ARM essentially licenses the core, and a lot of semiconductor vendors have licensed that architecture. Basically, the architecture license is taken, and they build the chip themselves. So it all conforms to what is called as ARM ISA or instruction set architecture, basically, which makes sure that it is compatible with other ARM processors others are making. So today, ARM is by and large the most popular one, and there's other architectures like RISC-V, which is an open architecture. RISC-V is like an open source effort for processor design. So that is slowly getting popular. There are today chips you can buy from some vendors like Renesas, others who have a silicon which is based on the RISC-V core. Hopefully it might become popular in the days to come because it's an open source, and many more companies are kind of embracing it. Even in India, there are some companies. I think the IIT Madras had a development of a chip which is based on RISC-V, and some people have licensed that core. And there was a company even 10 days back. There was an article about it. They have made a silicon out of the same RISC-V based core. There's a Shakti core which IIT Madras designed. So there have been people who have adopted that and using it. So RISC-V might become popular in the days to come. We have to wait and see. But slowly, commercial chips are available. Maybe 10 years back it was not there, but it was mostly academic and research, and universities were kind of looking at it. But today there are companies which are making silicon based on RISC-V. But if you look at the current existing designs, ARM probably is the largest in terms of popularity. Okay. And typically, if you see, most of the times the boot code will be in either a flash memory, which is probably on the microchip and the controller itself. So many of these low-end microcontrollers have a small amount of what they call as flash memory, code flash, data flash, and all that. So the boot code will be built in. Many times the processor vendor themselves will give you the basic boot code, and using that you can actually program the flash. On the chip itself, on the single silicon, you have the processor. You also have a small amount of what they call boot ROM, which the semiconductor vendor themselves gives some code for that. Then they have an on-chip flash where you can store code and data and all the other things. So what normally happens is when the system comes up, the boot code which the vendor has already provided starts up, and through an USB port or a UART or a serial connection, you can use an external programmer and you can download your program into the flash memory. So the boot code helps in doing that, because as we saw earlier, right, when the processor starts up, it will always jump to one fixed address. So at that address, there has to be some memory which is having proper instructions. So that is generally achieved by putting some kind of a non-volatile memory at that address space. And normally it will be a ROM of some kind or whatever. They have a boot ROM. Most of the microcontrollers will have a boot ROM which already has proper code which starts up the system, and it will come and initialize a few peripherals. After that, you may be able to communicate to that boot ROM code with some serial port or whatever. Then if you want to download your own program, using that boot ROM program running on the microcontroller, you will send the new instructions. Basically, it is in some format, you send it. That will then program it into the flash and then give control to that program. So that's how typical development happens actually. So essentially, most of the microcontrollers, sometimes if you're using a higher end microprocessor which doesn't have too much of on-chip thing, on the system, on the board, you will have a boot ROM or a flash where there's a boot code which is available. So when the processor starts up, it will go to that address and pick up that and execute it. Then the subsequent additional application programs can be loaded actually. So typically that will always be there. And most of the times there's a good amount of peripherals supported on the chip itself. Microcontrollers come, typically a microcontroller is nothing but you can say a microprocessor with a lot of peripherals and some amount of on-chip memory. That's if you want to distinguish between what a microprocessor is and microprocessor is nothing but the CPU, which is the ALU and the bus control and all that, which is only job is to execute instructions. Whereas a microcontroller will have a CPU, which will also have a typical set of peripherals around it, and it will all be on a single chip, so the cost is low. So if you want to build a simple system, the microcontrollers are generally useful, and that keeps the cost really low for the entire system. And if you look at the software, the complexity, there's a huge spectrum from simple, tight loop kind of a code for a very simple device, or you may have a high-end embedded device running Linux and supporting a lot of peripherals and interfaces and so on. So the entire spectrum is there. In between, you have the real-time operating systems and other sometimes homegrown. As I talked about, some big companies may have their own operating system. Like Cisco, if you take all their routers, they have their own operating system. So many big companies have their own platform which they have built over time. So they kind of continue to build and use that to build the systems actually. Okay, so that's the way. So typically, yeah, this is a typical architecture. So what we'll do now is we will kind of look at a sample microcontroller from Renesas. So this is called R4AM1, which is a series of ARM-based thing. This is based on the ARM, you can see here. This is the entire block diagram of the processor. You can see here, ARM Cortex M4. This entire block represents, this rectangle here, represents the ARM Cortex M4. So M series of processors from ARM are microcontroller class processors, which are like, slightly lower end processors, low memory, low speed of execution, good for microcontroller type of applications, okay? And this particular variant chip supports DSP. See, the ARM architecture has several instruction extensions, okay? It supports what is called as a DSP. DSP stands for digital signal processing. So which are used to implement things like your codecs, right? If you have a MPEG-3 or MPEG-4 codec or MP3, any of those digital signal processing, you need special instructions to be efficient and fast. So this particular implementation supports the DSP extensions. It also has got a floating point unit. So you can have processors, very simple microcontrollers, which may not support floating point. See, floating point is needed only when you want to do some numerical computations and stuff like that. Many a times, if it's a very simple application, you can just use integer arithmetic. If your precision requirements are not very high, you can just use your integer arithmetic and actually implement it. So then you don't even need a floating point unit. So there are some variants of microcontrollers where you may not even have a floating point unit, whereas this one, it has the basic ARM Cortex M4 basic instruction set. It has the DSP extensions. It has got a floating point unit also. So all or both these extensions are supported. And then it has got what is called as a MPU. MPU stands for Memory Protection Unit. Okay, so Memory Protection Unit is used to ensure integrity of the programs and data. So you can actually define if you go and read the a good way to understand all these microcontrollers is to go and read the data sheet. And there will typically be what is called as a hardware reference manual. Be huge, but you can read section by section to understand. It will give you a description of what is the functionality of each of these blocks in this diagram. There may be some 8 or 10 registers to control the functionality of each one of these. If you see the MPU, they are defined you can define multiple regions. And you can see whether, when you say region, memory has a range of addresses, right? So assume my memory is from 0 to 4 GB or something, just for an example. Then I might have defined some regions in that. So I can define a start of region, end of region. And I can say like, okay, each one, what needs to be done. So we'll go into more detail. Each slide, there's a slide for each one of them. Then this is called the vector interrupt controller, NVIC. Then you have a system timer, which is for the system level timing. Then you have a test and debug support, like when you want to connect a debugger and work with it, right? There are standard interfaces which these architectures define. There's something called R, core side, debug, port. There are multiple standards which are there. So it supports those to kind of support debug. Then there is something called as a system block. The system block has some basic initialization registers, which are typically need to be configured before you start using it. Then this is a memory block where you have the different types of memory. So this is a memory block. We'll go into each one later. Then you have a DMA block. DMA stands for direct memory access. Then you have a set of general purpose timers and things to do with some PWM control here. Then you have a good amount of peripheral interface, communication interfaces. So like I2C, something called a standard serial communication interface, which you can program to be like a UART and other things, serial peripheral interface, many devices here. Then you have things to interface with the capacitive touch sensing unit, or as a segment LCD controller. So you can, this is used to, if you want to have a display for your device, right? You can use this to connect a LCD panel. This can be used for a touch sensitive, capacitive touch sensitive unit. Then you have some things to, event link is something to do with how you deal with events and interrupts. There is a dedicated block for security algorithms. These are all hardware implementations actually. Then this is also related to accelerating some common functionality which you do in data processing. Then there's an entire block to deal with analog and digital conversion. We'll talk about all of these. So typically all these are part of this chip. So as you can see, this is a really highly integrated microcontroller which has a lot of peripherals. So this is called, I think this block is R4AM1, I think it's called R4AM1. You can Google this and you can look at the data sheet. It's freely downloadable. You can download it from Renesas website. The entire hardware user manual is available. So you can go through section by section to understand how to deal with that device, what are the functionality, how to program it. All that is covered in that manual. So it's a huge, will be some 1,500 pages. A chip like this with so many peripherals, a huge manual, but you deal with what you need, read section by section. That's when, so if as an embedded system designer, you have to be able to understand the hardware. That's an important skill. Like if you are doing application level programming, you will probably worry about all these things. But if you're doing a embedded system design, if you have to design your system, you have to timing constraints to meet, you have to know what resources I can use here, how do I communicate with the external devices and all that, right? So this skill becomes important. So you have to kind of go through the instruction hardware reference manual, or sometimes there will be something called as a programmer's reference manual. Different companies call it by different names, but all of them will give you good information about how to do this. And many processor vendors today also give you a good amount of software. For example, Renesas, if you look at it, they give you what is called as a flexible software package. Like they have given code for almost all these peripherals to do the basic initialization and basic use of those peripherals. So you have the reference manual for reference, but they have also given you some good amount of code which already deals with all these registers and does the basic operation. It may not exactly meet our requirements, which in which case you may have to go and write some additional code, but for most cases, that's a good place to start. Instead of starting from scratch by looking at the registers and trying to figure out everything by your own, many of these come with a good amount of software. For example, Renesas has this called FSP, they call it Flexible Software Package, which the code is open source, it's there in GitHub, you can go download it. You can actually go through that to understand also how each of the peripheral operates. Suppose you read the manual, you don't understand that manual very clearly, right? Then the code is also there. You can go and read the code and see what exactly is the code trying to do. So it takes some time to figure out the code, there'll be a lot of files and all that, but once you understand the overall architecture, it is a good step to start understanding the device better. Most of them today give, because it's also a competitive advantage, right? As a semiconductor vendor, Renesas is one vendor, there is Microchip, there is NXP, there are so many people selling very similar parts, right? So for them to ensure that more and more designers choose their parts, they try to make the process easier. So it's in their own interest to give that software, because then as a designer, if I have to pick between two parts, right? One guy is just giving me 1500 page data sheet, go read, figure it out. Other is giving me that plus a good amount of software to refer and use for basic things. I'm obviously going to choose the other one, right? Because everybody is running short of time. So it's always good to do. So most vendors today support it, and they will also have some support teams and all that. If you still are not able to understand how to use a particular peripheral, they also give you what are called application notes. Like for each of these things, they'll give you some sample implementations, how to use this particular functionality, how it can be implemented. So generally, semiconductor vendors support with a good semiconductor company will provide you a lot of support for the designers by reference code and specific queries. If you have some special query on saying this, how do I interface, is this working, will it work or not, there will be teams sometimes to help you out. Again, you may have to sign up for a support package for that, but generally support is available to do a good design. So this is just the top level view of this microcontroller. So we'll now look into each of these sections, so that we'll not go into too much detail, but for you to get a flavor of what each one does, we'll go through them now. So the first block we talked about is the CPU block, right? On this microcontroller, there are a lot of peripherals, but the core of that is the CPU block. And as you can see, it's an ARM Cortex M4 chip. I think most of the versions of this, I remember it was running at 48 megahertz. It's not a very high speed chip. It was running at some 48 megahertz speed. Okay, and it supports, as I said, it supports the floating point unit, and it also supports the DSP extensions. So it is good to use for applications. So what does it mean? Suppose I want to design, say, some camera application, right? And I want to process the video which is coming from the camera. And I want to say, camera gives me a live feed. I want to say, encode it into MPEG-4 and store it, because I want to store it in a compressed format, right? Because the space is huge. So if I want to design an embedded system for something like that, obviously this processor may be a good choice because it has the DSP support. So the encoding, MPEG-4 encoding algorithm may be able to run on this because of the support. Otherwise, 48 megahertz may not be enough to do the compression, encoding operation, for a decent sized input. But if there's a DSP support, maybe it's an efficient implementation. I can then probably implement that encoding algorithm on this processor, or maybe some audio processing I'm doing. Say, assume I am trying to do some speech conversion or something like that. So all these matters, like if I am choosing a device, I'll be looking at all the functionality and choosing the embedded device which supports my application. This is again the example of that tight coupling, right? So the device you choose depends on what you want to achieve. So if my application, I am not worried about all these things, then maybe if there is another component from Renesas which doesn't have all this, but it's even cheaper, that may be good enough for me. So it again depends, right? If I'm just running a small remote control unit, this may be overkill. But for example, I have this Alexa type of remote where on the TV itself I can press a button and speak, and it does some processing and sends the data, right? Then something having this may be a useful option. So it's again, ultimately, it's the target application which decides what to choose. So this example unit that we had does support DSP, so it's good for probably some of those applications again. Again, speed is still not very high, but for a particular class of application, this DSP may be good enough actually, okay? It has this memory protection unit. We'll talk about it, what all it does. Primarily, it also supports what are called stack overflow underflow detection. So one common mistake in programming, right? So you have allocated some space for the stack. So normally in a running program, stack is consumed, like if you keep calling functions. So whenever you call a function, some amount of space is allocated on the stack for local variables and all that, return address and so on. Now you keep calling nested calls, right? You may soon run out of stack, or there is some error in the program. So you return a recursive code for some reason, and the recursion end condition is not happening. So then the stack will keep growing very quickly. Or you having an interrupt, nested interrupts are coming. This huge number of interrupts come, it's a nested call. So the stack depth becomes very high. So if all those kind of scenarios, what happens is, the stack may overflow. So I think this has some built-in unit which keeps, you can actually program some registers initially. Like as a designer, when I finalize my program and code and all that, right, as part of my initialization system, I know this is going to be my code. This is the range of stack I've allocated. So I will go and program these registers, stack, overflow, underflow, the boundaries. Maybe the stack is, say, I've allocated stack addresses from, say, 0x, some address to another address. I'll go and program these registers. Then what happens is the program keeps checking. Whenever there's a stack operation, the hardware keeps checking. And if it exceeds, overflows or underflows it, either it goes below the address or above the address, it will immediately give an exception or an interrupt or whatever, and you can deal with it. At least because if something like that happens, you may be corrupting other parts of your memory. See, in memory, it's a continuous range, right? You allocated some portion for the stack. Maybe above that you may even have code. Below that you may have probably other data. So suppose the stack is exceeding in either direction. Either you may corrupt your code or you may corrupt your data, right? Without knowing. So the stack, so that is also part of the memory protection unit. They also give facility to define multiple ranges. And for each range you can specify, whether read access is allowed, write access is allowed. So if you want to protect some regions, like for example, I have kept some data which should not be modified during the course of the program. Assume some constants, which I don't want it to be changed at all, right? So I want to keep it, it's not in ROM, but it is in RAM only. But when the program is running, I don't want anybody to modify that. So maybe I can define a memory region and say this memory region is read only. Then what happens whenever accidentally, assume in C you have declared a pointer, you messed up that pointer, so now that pointer is pointing to that region. Then this will catch it and tell you, there is a write access attempted. So memory protection unit is good. So it's the simplest form of unit. Advanced microprocessors which have to run operating systems like Linux and all that, they'll have something called as an MMU, which is a memory management unit which supports things like virtual address, physical address and all that. This doesn't support a virtual address kind of thing. This is more about protecting some memory ranges, protecting against stack overflow, underflow and things like that. But it's still a useful functionality because you can protect certain ranges from corruption, which can be difficult to debug later actually, okay. Then you have what is called as a nested vector interrupt controller. So basically it supports nesting of interrupts, like one more interrupt comes, it can handle that. And vector means, it can automatically route it to the right interrupt service routine, because I said when an interrupt comes, you have to go and execute a particular interrupt service routine. This gives you a way to route it to the right one. So this is part of that system unit, system block. Then there is a system timer which is used for, maybe the system timer may be used for things like the operating system. It can generate some what is called as an OS tick, like for scheduling and all that may be used. And it supports all the debug interfaces, because the debug interfaces are important for you to kind of connect with the debugger on you have a board and you have your IDE is running here, your Eclipse or whatever, right? The vendor's IDE is running here. How do you connect to the board and debug? So there are some standard ports given on the board through which you can, some JTAG based standards are there which you can connect and you can debug actually, okay. So these are the part of what we saw as this ARM Cortex block. That's what we have seen here. So we have finished the ARM Cortex block. Then we'll move on to the next block here. So next is the memory block. The memory block is here. Can you see this is the memory block on the chip. As you can see, there are 3 blocks internally. One is called the code flash, another is the data flash, and there is an SRAM, right? Okay, so these are 3 things there. So this chip doesn't support an external memory, because if you see the pinout, there is no external bus coming out to connect a external RAM or a ROM or whatever. So all the code that you want to write has to fit into this memory which is on the chip. And it supports a decent size. It supports a flash memory where you can download your code. So it supports 256K of code flash, and it supports another 8K of data flash. So basically all your instructions have to be kept into this code flash, and additional data that you want to store permanently or use it for some purpose, you can keep it in the data flash. Then it also supports SRAM. I think it supports 32 KB of SRAM. 32 KB of SRAM it supports. SRAM is for things that are, like for example, all your variables when the program runs, right? You need some memory to keep all your variables so that the code can modify, read, write, right? Because variables typically will be reading and writing. So it has to be in RAM. So typically all the variables will typically be put into RAM. Sometimes you may even move part of the code to RAM for execution speed. Sometimes the execution from SRAM is faster than the flash. So some devices support that. Here the most common use in this case would be to keep some variables on the static RAM so that read and write is faster. So this is the memory block. So as you can see, it's not a lot of memory, right? 256 KB is not a lot. So these devices, PC has some 8 GB minimum nowadays. Whereas compared to that, 256K is a really small size. So that's where the code has to be really compact. You have to really, that's the challenge when you talk about flexibility you're asking, right? I mean, it's like changing something may not be very easy because the memory itself is very limited. So you take this device, build for a particular application, you'll be able to just about probably fit it into the flash memory and let it run. If you have to change it, first thing you probably have to check on this device is to see whether is there enough memory available. If I add to support another functionality, can all that code fit into this? So that's the challenge you will probably have here. And speed is also not very high, 48 kilohertz, but memory is also quite constrained. So you have to probably be able to fit everything into the code flash to run the program. Okay. Then the next block is called the system control area. So this one is here. So this is called the system control area, the one that I'm highlighting here. Okay. So you can see several internal blocks within that. But system control area, broadly, you can understand it is to initial setup of the CPU itself, right? Like typically you will have multiple clock inputs coming. You can set the speed. There may be something to do about the clock trees are to be programmed properly for each of the device, which clock you want to choose. Then you will have to decide how to handle resets or NMI, certain conditions, whether a reset should come or a NMI should come, power management. There are a lot of very, what you can say, system level functions, which are not very specific to an application. All those things are typically part of this block. And this block will typically be programmed by the initialization code. When the processor starts up, right, one of the very first things to do would be to make sure each of these units you see here, right, you can see within this so many units. Like for example, you can see this entire block is about clocks. Like multiple clocks there's some M oscillator, HO, CO. Each of these, maybe there are different peripherals within other peripherals, maybe using one of those clocks. So you can decide which clock to use for what. So you'll be programming those. Then there will be, for example, power control block. Different processor modes may be there. A sleep mode could be there, how to put a processor in sleep. Then reset. When a reset happens, there may be some registers which tell you why the reset was done, whether it's a soft reset or a hard reset, or the reset is because some watchdog timer expired. So for each of these blocks, when you go read the manual, you will see a lot of set of registers. And this block mostly will be managed by the initialization code. It is not very specific to one peripheral. Mostly the system startup time only, you will have to program all these blocks for proper operation of the process subsequently. So that is why it's called a system block. You have things like register write protection, battery backup mechanisms. So many functionality is part of this. It's a huge block with a lot of functionality. But yeah, you can go through I would strongly suggest all of you to download this data sheet, the hardware manual. Don't worry if you don't understand the whole thing. At least kind of browsing through that will give a good idea of what really is there in that document, how to understand. There will be timing diagrams. All these blocks will have some register descriptions. So you'll get a sense of what is there. And then you'll be able to probably, you may not understand all of it in the first instance, but you'll at least get a sense of what is there in each of these blocks actually. Then the next block is called the direct memory access block. So on the diagram, you can see this here. So there are two sub-blocks. One is called DTC, which they call it as a data transfer controller. And there is a set of DMA blocks which are used to program the whole access. So DMA stands for direct memory access. See, normally, direct memory access means you don't need the CPU to do the data transfer. Like for example, a peripheral, one of the peripherals, you have so many peripherals here, right? So you can see in this, for example, let us take this example. There is this USB FS, which stands for USB full speed. There's a USB full speed peripheral available on chip. Now, say assume this device is connected to some USB stick or something like that, right? And it is trying to read from there. Now, if I have to read some 100 bytes from the device and store it into, say, the SRAM temporarily, that is where the program wants to read it later. If there is a way for me to directly do it, put it into memory without, for example, the other option would be what? I read 1 byte or 10 bytes, put it in a small buffer, then I interrupt the CPU. Then the CPU can come read those 10 bytes from this register, and it has to go write it into SRAM. So that is called CPU-based copy. Like I get 1 byte or 4 bytes, I store it in a temporary buffer, then the peripheral will interrupt the CPU. The CPU's interrupt service routine will come. It knows USB has interrupted me. It will go and check or receive data has come. So it will go read those 4 bytes. Then it will transfer, it will do a write into the SRAM. So here the CPU is involved in the process, right? And this can be inefficient because the CPU will be loaded with this data transfer, read, write continuously. So most modern architectures will support DMA. So here, once the way it will work is normally, you will program the DMA block saying that, okay, read from this peripheral and write it to some address in memory. So both the read and write addresses you'll be able to program. And then automatically the DMA engine, once you program and let it start, it will go read it and copy it back. So basically, that is the advantage of DMA. And most modern, even high-end computers, everything will have DMA. If you look at a PC kind of a thing, DMA is what is used for almost all the IO, because otherwise the CPU will be burdened with a lot of the data transfer operations, which is costly. So DMA block supports that. Again, especially it's very important because the CPU, as I told you, it's not a very high speed CPU, it's a 48 megahertz CPU. if you are loading it to copy data coming from USB full speed, the CPU may not be even be able to keep up with the speed of the data. So it's good to have a DMA block. So the DMA takes care of the data transfer from to and from both sides actually. Okay, so that is the DMA block. Next thing is the timers. Okay, so the timer block is here. You can see this block here. This is the timer subsystem within the Renesas chip. Okay, as you can see, there are something called GPT32, GPT16, AGT, RTC, WDT, IWT. These are different types of timers. We'll quickly see a few of them here. So one is the most important thing. One is called the real-time clock, which kind of keeps track of the real time actually. And you will initially program it, and then it will keep maintaining it as long as the system has the battery power and stuff like that. It will work actually. Other than that, it also has a lot of GPT stands for general purpose timers. So general purpose timers is something where you'll have an up counter or a down counter. For example, you can go and program the timer, and it will keep counting, and either it overflows or underflows. It will either generate an interrupt or indicate you in some way. And again, there are many ways to control the timer. Maybe I'll just show you some examples here just to illustrate that. See, for example, right, you may have a, let's say you have a 32-bit timer. Okay, so this is a 32-bit. It's actually a timer. You can imagine it like a counter. Assume, for example, I'm not sure how this device does it. For example, it could be a down counter, right? Okay, so I initialize this 32-bit counter. The maximum I can initialize is say 0xFF in hexadecimal. This is the biggest number that I can store here, right? Now, the moment I load it and the counter is enabled, there may be a bit there may be a register which says enable the counter now. Then it will start down counting from FF. It will be FE. It will keep counting down to 0. Now, there may be other things to program, how fast it counts also. That is where some of all your clock controls will come in. You can decide, what clock to feed this. Maybe the system clock is at say 48 megahertz, right? So 48 megahertz means it can count, what is 48 megahertz? 48 into 10 power 6 clocks per second, right? So in 1 second, it would have counted so much. So even if you have a 32-bit counter, it may not last too long. So sometimes, if you want a larger counter, there may be a way to change the clock which drives this counter. There will be some programmable dividers. They are called clock dividers. You can say divide this clock by 2, 4 or something like that. So what happens is the clock which is used to count itself will come down. Then you will get a longer duration. So basically this is where all the embedded system design when you based on your application, right? If you know I need a timer for say 5 minutes, right? A 32-bit counter at this clock speed may not directly give me a 5-minute timer. There may be pure software ways to implement it. One way to do it would be what I can have one variable. Okay, I can say initially I initialize it to 0. Assume this counter gives me maximum say 1 minute possibility. With the 48 megahertz clock, FF gives me 1 minute. What I mean is like in 1 minute this will become 0, I'll get an interrupt. When the interrupt service routine comes, I can come and increment this variable from 0, I'll make it 1. The next time the interrupt comes, I'll immediately reload this counter. Then another interrupt comes, I'll make it 2. So finally when this becomes 5, I can go and do the job which needs to be done every 5 minutes. That's one way to do it. Other way would be if I don't want to do this overhead, if I can change the clock ratio to a lower clock, then the single counter itself I may be able to program an exact value so that I know when the countdown happens, it is exactly 5 minutes and I can go and do the job. So it again, system gives you multiple ways to do the same thing. You're getting the idea, right? Either you can implement your own second level counting with 1 minute counters, or you change the clock, you may be able to change the frequency. So basically you have several counters to do these kind of general purpose counters, and it also has something called PWM waveform. PWM is like pulse width modification. I mean basically it's a way of motor control and all that. So using these set of counters, you can program it with certain modes, so it generates some output which can be used for PWM control. So there's an entire section in this chip which is dedicated. So I think this chip is probably popular in motor control kind of applications, right? There are some types of motors like BLDC and all that, where today these fans are becoming popular, right? You might have seen the BLDC fans. So you have the BLDC fans. Have you seen BLDC fans? They're getting popular now. The old induction fans are slowly going out of fashion. BLDC stands for brushless DC motors. So they are supposed to be more power efficient, and they all come with a small remote. In fact, that fan has a microcontroller by itself. You get a small remote, you can change the speed, and I think those all need some kind of way to control the speed using some of these pulse width modulation type of techniques. So this chip supports some of those. Then it has called something called as a watchdog timer. So watchdog timers are generally used to make sure the system is healthy. Okay. So what does a watchdog timer do? Watchdog timer is essentially, the concept is something like this. Say in any healthy system, right? I mean, in any embedded system, you want to make sure that the system is healthy. When I say system is healthy, it means that the program is not stuck endlessly waiting for some event to happen, or it's not in some infinite loop, not responding to user events. So generally, what embedded system designers do is you try to have something like a health check. Like if the processor is working normally, if it's a real-time embedded system, right? There will be one task which has to run every 1 minute or every 5 minutes or something like that. It has to come and do something periodically. And if the task is not running, then that means something is wrong. See, if you have designed a system properly, I mean, I'm just talking about a scenario where it's like a multiple tasks, or a real-time operating system scenario where you have multiple tasks running. The tasks will have different priority. So ideally, as a system designer, you have designed it in such a way, you know that even this lowest priority task should get a chance to run every once in 1 minute, for example. Maybe there are a lot of higher priority things to happen, but as per your system timing calculation and all that, everything should get completed. So in a 1 minute window, this task should get CPU time to run. Okay, now you want to make sure that it is happening properly. If that is not happening, you want to recover. See, the easiest way to recover in an embedded system is to reset it. See, at least once you reset, all the old data is lost, state is gone, so you at least restart from a clean slate. Unless the same set of conditions happen, probably the system will run properly for some more time at least, right? So the easiest thing in a system is to restart the system. So how do you achieve this? We use something called as a watchdog timers. See, watchdog timer is again a timer which is nothing but a counter, okay? So it's just a counter. You can load it with some value. Say I load it with some value, say 0x3ff, and it typically again down counts to 0, right? Now, the way this is called as a watchdog timer, this has got two timers. One is called as a watchdog timer and another is called independent watchdog timer. I think the only difference is the clock input for these two are different. Independent is completely independent of all the other clocks, so which is a little more reliable if you want to really use it. Here, this may depend on the other clock sources and all that. So both the things, the way the thing works is, the moment you load the counter and enable this watchdog timer peripheral or subsystem, it will start counting to 0. If you let this counter reach 0, by default, the system will get reset. The microprocessor will actually reset and go back to the reset operations. Or you can program it to generate what is called as a non-maskable interrupt. Very often in a non-maskable interrupt also is you will probably reset the system and restart the system. Now, to make sure that things are normal, I talked about one task, right, which is supposed to run, say, every 1 minute. What the task will be doing is, it will come and do what is called as a refresh of this counter. A refresh is nothing but you may have to come and read or write some registers in this subsystem. Typically in this processor, you have to go and write some 2 bytes to one register. The moment you write those 2 bytes, it's fixed pattern, some 00, FF or something you have to write. The moment you write, this counter is reinitialized. So suppose it had counted down to say 0x100. The moment you go and do the refresh, this counter will again start from 3FF. And you assume this whole count from 3FF to 0, let's assume based on the clock input I have given, this is taking say 1.5 minutes. Okay, and this task which I am having, which is doing the refresh, the way I have designed the system, I am sure this should run at least every 1 minute. Okay, then if by any chance this doesn't run every minute, what will happen? This counter would have counted down to 0 and the system would have got reset and the system will restart. Sorry, understanding? So this is how a watchdog timer is used. So this is all calculations that will be done by the embedded system designer. You have to know, if I program it like this, what is going to be the time. Based on all the other things I need to do in my embedded system, I should be clear how much time all the other tasks are going to take, and will I be able to come and refresh this within a 1 minute window. So once you have done your design and testing, you know that it is working. But later, when you are distributing the device, somebody is using it, some condition, exceptional condition happens and this doesn't happen, right? Automatically the device will get reset and restart. In most embedded systems, a reset is better than the system hanging, because at least it will come back to work, even if it's a router or whatever, right? That's what they do. If something happens, you want to quickly reboot and start handling packets again. So it will minimize the entire downtime. Because if you're stuck not doing anything, you'll be losing packets forever. So most even communication devices will all have a watchdog timer setup. Moment something is amiss, like 1 minute something has not happened, then automatically the device or the router or whatever will get rebooted. Then once you reboot, typically you are at a clean slate, you will start handling it. Unless the same condition happens again, probably you are okay for some more time. So watchdog timer is an important functionality in many embedded systems, and critical systems will definitely have a watchdog thing. And this is how it works. So the watchdog timer subsystem supports by giving some counters, and you can program it, and there are more things. You can even set some more windows within this range where this watchdog timer refresh should happen. If you want even more tight control, right? I want it to happen in the first 25, I mean, like this is counting from say 3FF to 0, which is say I said it's a total of 1.5 minutes. If you want to make sure that this event happens the first say 30% or whatever, right? Then I can set some window in the refresh register. The refresh has to happen only between some 3FF to 200 or something like that. Within that it should happen. Otherwise you'll get a general error. I mean, that error can be used to track, whether your system is behaving normally or not. You may be even counting those errors, so you'll get a sense of, how well your system is designed. So those are called refresh errors. So you have designed the system. You think this timer should be running within that window, but you can track. You can put that window and say, if the refresh is happening outside the window, give me an error signal. And you can count the errors. Then you will get a sense of, how much you are violating your own timing constraints that you are set. So these are all essentially, hardware blocks which help the embedded designer to manage the timing and overall control of the system so that you can build a very tightly controlled and predictable system. Is that clear? So that's the watchdog block actually. So as I said, right, this is what we do. So it is very useful to restart the system automatically when there are issues which cause the software to freeze or in some endless loop. So this is how we do. We design a software to reset the watchdog periodically, and if the reset does not happen and the system will stuck in some process, the entire reset will happen. So which is good to recover to a known state actually. Okay, so that is the timer block. So you can see all the blocks here. There is many more. You can read the manual for more details, but these are the important. GPT is the general purpose timers, WTT the watchdog, this is a real-time clock, and we have a few more also there actually. The next block is called, the communication interfaces block, which is here. You can see this block. This is the communication interfaces. So you have multiple sub-blocks within that. So we'll quickly now look at what are there in that actually. What are the sub-blocks which are there here? Okay, the first one is called SCI. I think it's called serial communication interface, which can be configured for many different peripherals actually. So one of the common things people configure that SCI, it's a programmable block, which means it can support multiple protocols. So you can make it work like a simple UART. UART is a RS-232C interface. You can program it to be like a UART, or you can make it like a synchronous, clock synchronous serial interface, or a simple form of I2C or SPI. I2C has many functionality. This can be configured to a very simplest case of that. Similarly, SPI also has many different capabilities. This can be configured to be very simple, the simplest configuration of SPI. It can also be used to support a smart card. You have the smart card interface. So this SCI is a programmable block which can be programmed for any one of these things. Most commonly, it is used when you boot up the system. The boot ROM actually puts that SCI in a UART mode. So you can connect a debugger to the UART or a flash programmer to the UART and download your code into the flash memory. So this is commonly used at startup time as a UART, but it can be used for many other, based on your application, you can use that. Then there's a separate full-fledged I2C port, which complete support for the I2C protocol. Similarly, it has complete full support for the serial peripheral interface, which is a popular serial interface protocol. Then there is something called serial sound interface enhanced. Older standard, there was a standard called I2S. Then this is a later one, which is a little more enhanced version of the standard. It's typically used to interface with sound devices, like audio devices. If you want to interface digital audio devices, you use this standard actually. Then there is something called CAN port. CAN stands for Controller Area Network. This is typically used in electromagnetically noisy environment. The protocol is robust for that. A lot of automobiles use it. Actually, CAN protocol is popular in the automobile world. Industrial usage are also there. So this again supports a proper CAN port. Then it supports a full speed USB port also. So these are all the communication blocks. And again, you can go look at the hardware manual to understand the full capability for each of these blocks. What are the registers? Each block will have an associated set of registers, maybe 10, 20, depending on the complexity of the block. You have a lot of registers to program. And as I said, the FSP, right, the flexible software package provided by Renesas, has reference code for all the blocks. So you can go to GitHub and search for the Renesas flexible software package. The entire code base is available, which gives you examples of how to program each of these devices, each of these blocks, and you can build layers on top of it to get the complete functionality. So this is the communication interfaces block which is there. Then the next one is the human machine interface. So the next one is the human machine interface, which you have here, which has two blocks inside. One is the capacitive touch sensing unit, and the other is the segment LCD controller. So as you would, like, basically if you want to have a touch interface to the embedded system that you're designing, right? Most popular touch sensing is capacitive touch sensing. So this supports peripherals which are based on capacitive touch sensing. And most popular one is an LCD display for external output for the user to understand. So there is something called a segment LCD controller which supports interfacing with an LCD. So both are, again, if you go read through the documentation for each one of them, it will tell you what are all the various aspects that you can program, and depending on the type of the panel that you're connecting or the capacity of sensing unit that you're connecting, you may have to program it appropriately to make it work actually. Again, example code is available, so that it's good to browse through that and understand how to use these devices. This is essentially, these are called human machine interface because either you are interacting to get input from the human or sending display to the human operator actually. That's why it's called as an HMI, touch sensitive capacitive touch sensing unit interface, and a LCD controller interface. Then the next block is the security features, okay, that comes here. You can see this small block here, right? It is called security. One of the main things showing there is SCE5, Secure Crypto Engine 5 they call it. Okay, so this SCE5, Secure Cryptographic Engine 5, the name they are given it for it, supports 2-3 things. One is it supports AES encryption. So AES stands for Advanced Encryption Standard. So there are multiple AES protocols, algorithms available. This supports the popular ones, and it is a very popular form of encryption used by many encryption packages. And the reason you want to have a dedicated hardware block for it, this is a dedicated hardware. So basically you send a piece of data, it encrypts and gives you back. Or you probably give it an address and it'll go encrypt that and give you back the value. So the reason you want to do it is, otherwise doing encryption by the main CPU itself is very costly in terms of the CPU cycles, right? Because encryption is a very compute intensive operation. You will have to probably look at, suppose I want to encrypt a 512 byte piece of data, right? Typically I'll have to go through each byte of data, then you'll do some operation. Generally they're called polynomial operations. You kind of do a mathematical operation with each of those bits, and then you finally get the encoded value. So the reason you want to do it in hardware is to reduce the load on the CPU, but you also want security. But today, security is becoming very important, right? Today, you hear so many cases of hacking, right? It's like your phone gets hacked, accounts get hacked, and especially embedded devices, there is a increased risk. There are cases of, countries hacking the other countries' systems. People talk about, some hackers from one country targeting the other countries, things like even power distribution systems, right? Today, if you look at a power distribution network, right, there'll be so many embedded controllers all around the thing. People are able to hack that enemy country's, power distribution grid and are causing a power failure. They are targeting those control units, hacking them and making the whole grid fail, or attacking, say, a water distribution system plant controller. They're all embedded systems everywhere. So you hack it, you stop the water flow for a city, you can cause chaos actually, right? So this is so many things. You have a security camera at home. You don't want anybody else to be looking at the streaming of that content, right? It is for your own privacy and safety. So security, embedded devices becoming very, very critical. IoT devices, you want sending data from your home to the cloud, you want it to be secure. You want the data to be encrypted and sent. You don't want anybody in between to be hacking into your data. Personal data, your wristwatch sends you medical data. You don't want somebody to tap that data and know about your health status and all. So essentially, security is becoming very, very critical in embedded systems also. So that's the reason every embedded device today has some support for security to keep the cost low and simple, because the CPU is not a very high speed CPU. If you load it to do all these algorithms, it will become much slower. So you need to have support. That's why there's a separate hardware block which supports this encryption. And that is how you're able to get the performance without compromising on the security. So generally, in general, in an architecture, dedicated hardware blocks are given to improve the performance and to keep the cost lower and the power lower. Otherwise, you have to run the CPU at a higher frequency. Or first of all, the chip, production itself has to be probably a different process which can support higher frequencies, which means increased cost. Increased frequency also means increased power, right? The chip burns power. If it's a higher frequency, you burn more power. So essentially, you want to keep the cost low, power low. Then the good way to do it would be to go to dedicated hardware blocks, because dedicated hardware blocks run only when needed and you use it only when you need that functionality. Otherwise, it can be shut down and kept in a power down state, right? So you use that AES block only when you want to encrypt something. So you'll go start up that block, give the data, get the encrypted data out, and you close it. So that way, these blocks help in implementing devices with low power and low cost. Then they have something called true random number generator. TRNG stands for true random number generator. Olden days, people used to have pseudo random number generators. Today, people are trying to use some underlying physical process to generate a true random number. So I'm not going to the details of that. There are some using the physical characteristics maybe of the semiconductor or the electron movement. They are trying to come up with something which are truly random. And there are, I think, some standards governing to test and make sure that whatever you have built is really passing those randomness tests. There are tests of randomness which you have to run. I think these guys Renesas has built a true random number generator which you can use. Random number generators are needed for many encryption and other algorithms for what is called seeding. Like you start your process with some value, and that value, if the other party, suppose everybody may be able to figure out what algorithm you're using, but if you don't know the seed, it is secure. But if you know the seed, they can actually crack the things easily. So people are using pseudo random number generators, but people found that is not secure enough. So this is called true random number generators, which are supposed to give a higher level of security. So you use those random numbers to typically seed some functionality, like some encryption algorithms you seed using that value actually. Okay. So random number generators need a seed. Even in C language, I don't know if you have used, there's a function called rand, R-A-N-D, right? Before you use rand, you have to use a function called srand. There's a function in C called rand. It generates a random number. It will give you a random number in some value. But to use it effectively, you have to do what is called srand. Otherwise, the default value it has, it will be a predictable sequence. So this srand is what generates that randomness. So normally in C or a general purpose system, most common practice is to take the system time in ticks and then use it because it's sufficiently random, you think. But if you want true randomness, I mean unpredictability and all that, so you use something called as a TRNG, which is a true random number generator. You will get a 32-bit value from that, and you can use that to seed your random number generator. So this is the use of the random number generators. Then they have something called as a unique ID, which is I think something built into the microchip itself as part of the manufacturing process, which is unique to that device. So again, these are things which can be used to what to say, like sign, for example, right? I am distributing software. I don't want that software to be moved to any other similar system. So I'm giving you firmware for say Renesas M4 chip. Ideally, that can run anywhere. But if I want to make sure that it runs only on this particular chip, right? What I may do is I may do some encryption of that software with some unique ID which is secret, and only it is accessible only to this device. So basically, only this chip, when it runs, will be able to decode that block and get the decoded instructions to run. So there are ways to prevent software from getting copied and all that. So unique ID is something which the chip supports, which is an data which is available inside the chip to kind of provide security in terms of your code or something not getting taken away to other systems actually. So these are again security blocks which are there. Then there is something called apart from security, these two blocks are, the CRC is more about data checks. When you, for example, when you are transmitting data, right? When you are receiving data, suppose I am sending you 512 bytes of data. Normally you do what is called as a cyclic redundancy check. Basically 512 bytes have been sent from there. So I take each of those bytes and I do some operations using all the 512 bytes. I'll get some value, maybe a 32-bit value. I do some processing there. That value will be also transmitted from the other side. If whatever I generate and what has been transmitted from the other, they don't match, that means there is a CRC error, which means there has been an error in the transmission. Generally, you use what are called generating polynomials to compute that, and they again use some mathematics. There is some sound mathematical logic behind that, and typically even a single bit error will be caught by that process. So you know that the data transmission has been proper. If you find an error, if you find a CRC error, that means you will have to ask for a retransmission. Most communication protocols will support some form of a CRC. So if you have to implement that CRC completely in software, right, again it's going to take a lot of time. So that is where again this block will help. So you use the CRC block to compute the CRC. You can quickly get a value and then you can compare and check whether the data has been transmitted with the integrity or not. If there has been a loss of data or has been an error corruption in the data, you can actually ask for a retransmission and get the data again. So the CRC blocks use in data transfer. So again, all these blocks, as I said in the initial statements, that these dedicated hardware blocks like security, CRC, all of them help in providing functionality without increasing the cost or the speed at which the microprocessor has to run, and without compromising on the security of the system. Okay, so these are important blocks today on the microprocessor, and they really help in building a secure device, which is becoming more and more critical these days actually. Okay.